I have explained various examples of cross-section balancing, and before giving the examples I have given the theory. Here I am going to talk about some additional materials on cross-section balancing from one particular research paper. So, what we have learned already will be finding use. We have already seen the method of area balancing in order to find out the depth of the detachment small h. So, with what we started? Consider there is a folded layer and due to a compression above a detachment, this fold is produced. Consider a pin line here, and to solve the problem finding out the depth of detachment, consider push has happened from right towards left direction. Now, before the push happened, this folded layer must have been a straight layer. So, one has to find out the length of this curved line, and the method I have already said you can break it into several small lines. After finding the length, draw the straight line in this way. So, this length is equal to the L0 length, which is the length of the curved folded layer. Consider the width of the anticline is L1. Note that the term width of the anticline is what new. You will not see in many textbooks of structural geology a term such as width of anticline. So, this is a term that has been used. L1 is the width. The moment L0 is straightened in this way, what we find is this distance is equal to L0 minus L1. So, that capital D is equal to L0 minus L1. We have already discussed these things. Now, find out the area bound between the curved line and the straight line L1. Let that be capital S. Then we can say that due to compression, here was the area loss and here was the area gain. Here the area of the rectangle is D multiplied by H. H is what we are going to find out the depth of the detachment. So, we can say S is equal to DH. This is true when no material gets added up during this deformation process, nor any material flows out during the deformation. Capital S henceforth we call as the excess area. Now, from equation 1 and equation 2, we can put this D value in equation 1, leading to equation 3. S is equal to L0 minus L1 multiplied by H. From here equation 3, we can write equation 4, small h is equal to S divided by L0 minus L1, that is what is stated. Now, through geometric measurements, capital S can be obtained, which is the excess area. L0 minus L1 can be obtained, and by applying the formula in equation 4, we find out the depth of the detachment. This method is not just theoretical, but it has been proved appropriate for certain experimental folds by structural geologists and also folds in the Jura mountain. So, for the real folds as well. In this exercise, we have considered a single level that got folded. What is the meaning of the word level here and where is that located? This line can be called as a level, and that level got folded. That is what is said. A single level has been considered, whereas we might find out in reality not just a single folded layer, but another layer also. So, in such cases H is a detachment depth from this particular point, and these two folded lines can be called as level 2 and level 1. There is a use of the term reference horizontal, which we will see. Now, we are going to see excess area graphical technique. What is the meaning of the term excess area? Here capital S is called the excess area. So, we are going to use a graphical technique where this capital S term will be involved. Here we are considering two levels that show kink fold geometry to start with. What are those two levels? This is level 2 and this is level 1. There are two levels. They have been kink folded. A kink fold is a fold with straight limb and sharp hinge. So, where the excess area graphical technique works, what is the aim? In such case, we want to know the depth of the detachment. To do that, we are going to use the excess area graphical technique. We have already seen from the previous example how to find out small h by using equation 4 when a single level was considered. So, for the two levels we can find out the excess area S2 for level 2 and the excess area S1 for level 1. What does this mean? For S2, this means this shaded area within the triangle, and for S1 this is the shaded area within the triangle. And using both S2 and S1 in this equation, what we deduced in the previous slide, here we can find out the H1 and H2 parameters respectively related with S1 and S2 excess areas. For level 2, for example, we can obtain H2 is equal to S2 multiplied by L0 minus L1 inverse, and for level 1 we can obtain H1 is equal to S1 multiplied by L0 dash minus L1 dash inverse. Ideally, H2 and H1 should be such that they give a single detachment depth. This is the one. In this diagram, note that S1 is less than S2. This area is less than that area, and interestingly H1 corresponding to S1 is less than H2 corresponding to S2. In nature, in this kind of deformation, folds more towards the skyward direction will define larger excess area S2 than what is at the depth as S1. Now consider orthogonal coordinate axis small h, the depth of detachment plotted along the x axis and the excess area capital S plotted along the y axis. The equation S equal to dH, which was demonstrated as equation 1 in this page, is written here. S equal to dH is a straight line passing through the origin and is comparable with y equal to mx. So, comparing S with y, h with x, we can say d is equivalent to m. D is called the slope of line. This means if this angle is theta, theta equal to tan inverse d. Now, as I explained here, from such a given diagram I will be able to find out an H2 value and an S2 value. From them I can plot a point here, and similarly using this equation I can find an H1 value and a corresponding S1 value, which I can plot here. If I join the origin, this point and that point, it defines a straight line S equal to dH. These 3 points, origin 0 0, this point and that point, what are their coordinates? This coordinate is h1 comma s1 and this coordinate is h2 comma s2 are collinear. That means they fall on the same straight line. The slope of the line S equal to dH through the data points is the displacement on the lower detachment. D is the displacement on the lower detachment. This detachment has also been called as the lower detachment. As I said, slope of this line S equal to dH is given by D, and that is equal to the displacement of the lower along the lower detachment. For level 1, capital D amount of displacement has happened. Along level 2, same displacement capital D has happened. I put forward a question, how far the natural folds show these geometric changes. We fully recognize that this is a model, and it will be interesting to find out the real folds, their profiles, and whether this perfect match that S equal to dH line drawn from S2 data and S1 data are collinear and that they pass through point the origin 0 0. Does it really happen with the fold? Note the equation, capital S is equal to D multiplied by H. What happens to the level 0? Suppose this detachment level itself I call as level 0. So, at level 0, H0 is equal to 0. Putting that in S is equal to D multiplied by H, S is equal to 0. What does this mean? This means that a line on the detachment Under this deformation, this compression does not get folded and capital S therefore, or we can call S0 becomes equal to 0. This now clearly means that as you go in this direction inside the fold, the S area keeps decreasing, S2 is maximum and then it decreases to 0 when we reach level 0, which is the lower detachment or simply the detachment in this diagram. So, H0 plots here at the 0 point of the origin. I am going to demonstrate, this is my addition. Considering such a genesis of fold, one can predict the nature of folding of other layers. What do I mean? Considering the excess area graphical technique, suppose I start with this level, let us call it level x, then this depth is equal to hx, and after compression the triangular geometry formed would be like this. So, this area can be represented by Sx. Using this graphical technique, we will be able to demonstrate at depth, that means from this point and downward, and for this level x what should be the geometry of the fold. If we consider all the layers are king folded and the king fold is progressively dying from this place towards the detachment. Now, if the level x is considered here, call it level y, then also we should be able to find out the area, excess area Sy and the height Hy. We have dealt with the king fold here, but similar concept of excess area diagram or excess area graph can also be extended for folds of other geometries. For example, consider round hinge folds developed over a detachment. In that case, this becomes the S1 area, this becomes the S2 area. We know how to find out the area of irregular geometries, we can do that, and using the formula S equal to dH, we can find out the respective H values. For example, this is H2, this one is H1, and H2 and H1 will be such that a single detachment depth can be obtained. So, for other fold geometries also the excess area graphical technique can work, but beware, I am talking only the ideal situations. Real cross sections I am going to demonstrate also during this lecture. Let us use the excess area graphical technique to find out the depth of detachment in a different way. This can be in fact a faster way of solving. We start with two levels that got folded, level 1 and level 2. Before deformation, level 2 say was of this length, and due to a compression it got folded, and before deformation level 1 was like this straight, and after deformation it got folded say like that. Instead of using the equation S equal to dH, choose an arbitrary reference level. Say this is an arbitrary reference level. We have drawn an arbitrary line in the cross section. From here find out the H1 corresponding to level 1 and H2 corresponding to level 2. So, these two can be measured. Now, measure S1 area and S2 area. This area within the triangle can be measured and this area within the triangle can be measured. So, they have also been done. Now, plot capital S versus H graph. This is the excess area graph where H is plotted along the x axis and excess area S is plotted along the y axis. H1, H2, S1, S2 have been obtained. So, this is H1 distance, this is H2 distance, this is S1 distance plotted and this is S2. So, we obtain 2 points with coordinates H1, S1 and this point H2, S2. Next, draw a line passing through HI, SI points. This line need not pass through the 0 origin. Once this blue line is drawn, it intersects the H axis and we mark this as the true detachment depth. From H1 to this distance can be measured and that distance is plotted over here. from h1 point to downward direction, or if I want to do it in another way, from h2 to this point, this distance can be measured, and from this place we can draw that line. Once this particular point is obtained, or by the previous method this point is obtained, I can draw a line parallel to the reference level and passing through that point, and this gives me the true detachment below the ground surface. We need to know what is the equation of this particular line. Equation of this line is S equal to d multiplied by h plus SA, and this line intersects the s axis at the coordinate 0, SA. This is the point it intersects at the coordinate 0, SA. Why? Because putting h equal to 0, I find capital S is equal to SA. So, the coordinate along the s axis where the line intersects is given by 0, SA. That is what is stated here. This SA equal to 0 means the reference level is the detachment itself. What does it mean? At the true detachment depth, suppose this is a level A, then this layer does not get folded by this compression, because this is the detachment surface itself. So, the SA becomes equal to 0, and that is what has been obtained. SA equal to 0 means the reference level is the detachment itself. This point coordinate can be obtained by putting S equal to 0 in S equal to d star h plus SA equation, which is here. So, if this is equal to 0, 0 is equal to d multiplied by h plus SA. Therefore, h value is equal to minus SA divided by d. Therefore, the coordinate of the point K is given by minus SA divided by d, 0. You have to remember this is the coordinate of point K. Now, let us understand this statement. True detachment can lie above the reference level. In that case, SA is less than 0. In this particular case, this is the drawing, and the detachment depth we have considered in this diagram a case of SA more than 0. This is the total SA distance, and this is that particular line. SA more than 0 is true when the reference level is chosen above the true detachment. We did not know where is the true detachment. We have drawn the line and later we found the true detachment, and now we understand that the reference level has been above the true detachment, and in this particular case this is the diagram produced. What will happen if the reference level is chosen here? That means this line is drawn, and then we have defined small h1 and here small h2. In that case, this would be the diagram, and SA will be less than 0. Where is SA? This is the intersection point between the line and the s axis. So, this is minus SA, and there is a third case when SA equal to 0. What is the case? When in this process, and this can be a rare situation, when in this exercise we choose the reference level exactly on the true detachment. So, that is the chosen reference level. Later on we find that itself is the true detachment. This case will be reflected in this graph as SA equal to 0, the line will pass through the origin 0, 0. Here the equation of the line will be not S equal to dH plus SA, but since SA is equal to 0, it will be S equal to dH, and this goes back to this particular equation and this simple graph. So, what we have learned in terms of excess area graph, let us apply it on a fault propagation fold. This line is defined as the upper flat, this line as the lower flat, and the slanting line, this one, as the ramp. We are dealing with upper flat, ramp, and then lower flat geometry for the fault propagation fold. A fault propagation fold has no displacement on the upper flat. What it means? We find that the layer is folded and no slip no brittle movement has happened. This is the meaning of the sentence, a fault propagation fold has no displacement on the upper flat. To understand the situation, different shades have been used to represent different layers. Here is a continuous black region and these are the two dotted regions. Different layers can be identified by the numbers layer 1, layer 2, layer 3, similarly 4, 5, 6 and 7, and those layers can also be tracked here in the footwall block. Layer 1, 2, 3, 4, 5, 6 and finally here layer 7. Let us consider layer 1. I highlight it with red color. I have marked layer 1 in the footwall block and also in the hanging wall block. If I draw it separately, how does it look? So, this is the fault and I have drawn it here. It is a reverse fault. I have added the symbols for reverse fault and the particular layer 1 of interest has been traced from here and here into here and there. Now, we want to apply the area balance method to find out the depth of detachment. Here detachment means this particular layer and its depth is not known. So, what to do? As we did in this classic Chamberlain method, we have to measure this total length and then what to do? This length has to be opened up. This means if this is A, B, C and D, find out the AB length, find out the BC length, find out the CD length, add them up, say is equal to AB length. This is point A. Now, extend this line here and reach this point on the fault plane, call it capital A and draw the AB length. Next, what to do? I have to find out the L0 minus L1 length, just like this diagram, which is here dB length. Where is dB? This is the dB length. So, that length has been obtained. Next, I have to find out this particular area. Now, note that the quadrilateral capital A, small a, B, C is a trapezoid. So, applying the formula of area of the trapezoid, we can obtain this entire area. Say this area is given by A0. Now, divide A0 by the dB length and what we obtain is the depth of detachment D0. This D0 can be drawn in this way vertically down from this line D0 and after getting that we need to draw this line parallel to that line. Once we do it, we have obtained the depth of detachment. So, here this A0 was the excess area and D0 is the depth of detachment. This has been done for layer 1. We can plot in the excess area versus depth of detachment for layer 1 this particular point. Now, what I have demonstrated for layer 1, do for layer 2, 3, 4, 5, 6 and 7 and plot all other points. In an ideal fault propagation fold, all these points and the origin will be collinear. So, draw that line. If not collinear, draw the best fit line. In case of a non-ideal fault propagation fold, points 1 to 7 will not be collinear and this is more realistic situation. I have already explained to you that from the line S equal to DH, the slope is given by D. Remember that and come back here. In this particular drawing case, D comes out to be 3.13 centimeter, but I want to alert you, tan inverse 3.13 is 72.28 degrees, whereas this particular angle in this diagram is only 37 degrees in figure 4. So, there is a problem with the diagram, maybe this is not to scale. A fold terminology I want to introduce, the detachment fold. What it is? Any fold above a stratigraphically fixed detachment horizon. So, in this case, this fold geometry can be called a detachment fold because here is the detachment or the lower flat over which the fold has been generated. Now, a detachment anticline, in this case, yes, it is a king fold and also a detachment anticline regardless of its internal structure. The internal structures are again folds, but of dissimilar geometries. They are not of similar geometry exactly. even if they are of various geometries, they can be of various internal structures, a straight line is produced on the excess area graph such as this.